Welcome back to another AP Physics 1 concept walkthrough. Today we're going to be working on two-dimensional equilibrium. So let's get into our facts. So these facts are pretty much the same as the first video, the one-dimensional equilibrium video. So if you did not see that, look at the dynamics playlist in the description down below. But just to refresh what equilibrium is, so this is when an object is either moving in a straight line at constant speed or it is an object at rest and all my forces must be balanced. And again, for any force, it is going to be touching or in direct contact with the object except the force of the planet on the object, which is known as the object's weight. So more of our facts here. So solving equilibrium problems, this is where this will change a tiny little bit here. We're going to draw a free body diagram again, but we're going to also work with forces at an angle in this video. So we're going to have to break it up into components, and we'll talk about that a little bit later. All the rules still apply for free body diagrams. So again, for the facts here, they're in the description down below for the entire unit, or you can just take a screenshot of this slide if you want to use it during this video. But again, everything, the questions and the facts will be in the description down below. So let's go into the second to last part. Mass and weight and normal force, that does not change. For this situation, we're not going to have anything in contact with a surface, so normal force is not really going to matter, but we're still going to be working with Fg equals mg. So again, if you want more detail on these facts, I went over them in the one-dimensional equilibrium video. If not, I'm going to still use them and explain them in this video as well. So let's get into the new part here, which is x and y components. All right, so x and y components. This is what we did not do in one-dimensional equilibrium. For any diagonal force, it can be written in terms of two perpendicular force components called the x and y components. Some teachers call these the horizontal and vertical components. They're the same exact ideas. Usually, the easiest way to do this, so the easiest way to memorize this, is when the angle is measured from the horizontal. You end up having the horizontal force be the magnitude of whatever force it is. So something at an angle, so this is like an example of this. A force at an angle is like this. So essentially, when I am talking about the horizontal component, I'm talking about this here, so I'll call this h. And when I'm talking about the vertical component, I'm talking about this here, so I'll call that v. So essentially with this, it's just like a triangle. Our angle is always going to be with the horizontal. And we're essentially going to be given, or we're trying to find the hypotenuse of that triangle. So the force here, where it talks about magnitude of the force, that is the original arrow that I drew, so that is the force here. And then we have the horizontal, that's going to be times cosine, because that's adjacent to my angle. And opposite of my angle is going to be that force multiplied by sine, and the angle, because that's opposite of my angle. So there's a little bit of SOHCAHTOA here, just fairly simple trigonometry, or if you haven't learned trigonometry yet, just an introduction to trigonometry for this. And all of the trig functions are on the AP Physics equation sheet, so you don't have to memorize them, but you probably have them in the back of your mind somewhere anyways. So let's get into our first of two examples. All right, so example number 1. An object of mass 300 grams hangs at rest as shown below. So my representation of this is this photo here. Tension in the strain pulling to the left is 4 newtons. So we're going to start off like we always do in any force question, no matter if it's equilibrium or not, and create our free body diagram. So again, the first that I can see here, last time I checked, gravity is straight downwards. So I can have here my force of gravity, Fg, going straight downwards. And again, when we do this, we annotate our free body diagram. So again, our steps for a free body diagram are in the facts, and the facts are in the description down below for the whole unit. If you're new to this, the force of gravity, or Fg, is not the force of gravity on the mass, but it is the force of Earth on the mass, because that's the actual object that's creating it. So whenever we have a force, It's the object exerting on the other object. So we have here what is creating gravity is Earth. So the force of Earth on our mass. All right, so then we have two strains here. So with strains, it has T2 and T1. You can keep it as that if you'd like. Some teachers do that. Sometimes since it's like a strain, you can make it FS if you feel like and just annotate it. For the situation, since they've given me T, I'm going to make it FT2 and FT1. So just going with the diagram that they give me here, or that I found here. So we have the diagonal strain is going to be like this. I'm going to call that FT2. Oops, let me fix that. So that's the diagonal string there is going to be FT2. And then the string that is horizontal is T1, so I'm going to call it FT1. And I will annotate those in a second. So FT2, I'll start with since I drew that one first. FT2 is the force of string 2 on the mass. So again, what is the object exerting a force on another object? So force of string 2 on the mass. And then FT1 is the force of strain 1 on the mass. All right, and those are all the objects in contact with my mass, and I obviously have the force of the Earth on the mass, so that's going to be my free body diagram. So with this, since I am at rest, it says that we are hanging at rest. In equilibrium, I need up forces equal down forces and right forces equal left forces, but all I see is a down force and no direct up force to it, and a left force and no direct right force to it. But I do have here at FT2, it's going both up and to the side. So that's where we're going to bring in our X and Y components. So that's what we're going to do here in part B. So let's move into part B. So in part B, we're going to redraw the diagram in part A, breaking the angled force into the X and Y components, and we don't need to repeat the list of forces here. So with this, we're going to have what we had here. So we have FG going downwards, and we have to the left here FT1. All right, so X and Y, X is horizontal, Y is vertical. So to make my FT2 into my X and Y components, all I'm going to do is make my horizontal X. So going this way, I have here FT2X. And going upwards, I'm going to have FT2Y. And it is really just that simple for your components. With components, do not draw them on the original free body diagram. That is actually a rule for the AP exam. If you're going to draw your components like this, just make another dot somewhere on the page, or sometimes when they have you make calculations, they specifically say do not add anything to the original free body diagram. They'll have you just write in that area. You can do that. That's what you're going to do here. So this gives us now our up forces and our right forces here. And when you look at that, we have up forces to combat our down forces, and now we have a right force to combat our left forces. So now we can actually create our equilibrium equations, which we're going to do in part C. So let's move into part C. And again, all this I'm doing here is taking the angled, and just essentially that's the base and the height of the triangle. My angled tension there is my hypotenuse. So let's move into part C. So again here, I'm just going to rewrite what I had there in the previous. So let me make my dot here, and we have here FG going downwards. I have to the right FT2X. To the left, I have here ft1, and going straight upwards, I'm going to have ft2y. Alright, so now I can make both my equilibrium equations for the vertical and the horizontal directions. So, for the vertical, that is up forces equal down forces. This is using our component free body diagram to do this. So the up force here is going to be ft2y equal to my down force, which is fg. And then right forces equal left forces. I have here right forces equal left forces for my horizontal. My right force is going to be, I can do left forces equal right forces. That might actually be a little bit better. So it goes along with how the diagram is. It's a force of habit to start with right. Left forces equal right forces. Let's go along with the free body diagram here. So we have here ft1 is my left force. And ft2x is my right force. So now we can go into the actual math here and get our tension in the string. So let's go into part D, which is actually doing the math. So we're scaffolding this a lot, going step by step so it doesn't get too crazy here. So we're going to go into part D now. So here's our actual calculation here. So to determine the tension in the angled string, we're going to use the equations we created on the previous page here. So we have here up forces equal down forces. And our up force here, to remind you, was ft2y. And then our down force was the force of Earth on our mass. And then we have here left forces equal right forces. Oops, let me write that a little bit closer here. So left forces equal right forces. And then our left force was going to be ft1. And then our right force was ft2 and then x. So now with our math here, up forces equal down forces. Our up force is what we're looking for here. So that's ft2y. We know that fg equals mg from our fact sheet. So then we can actually get our number from here. So let's do this one real quick. So ft2y equals, my mass is 300 grams. Convert that into kilograms. That's 0.3 kilograms. And then g we know is 10 newtons per kilogram. So plugging this into my calculator here, I'm going to get a very simple number. 0.3 times 10 should end up being 3 newtons. So let's just make sure we have a calculator. Let's always make sure we get the correct number. So 0.3 times 10 is going to be our up force here, which is going to be 3 newtons. So ft2y is 3 newtons, and left forces equal right forces. This one's pretty easy. They tell me that the strain is pulling to the left with 4 newtons. That's going to be ft1. So 4 newtons equals ft2x. So essentially right now, we want to find ft2. That's going to be at an angle. And we found here ft2x. And we found ft2y. This looks pretty similar. ft2 is essentially the hypotenuse of my triangle. And we found the base and the height of the triangle. So if I have 3 and 4, if you know your trigonometry, you know what FT2 is going to be already without doing the numbers, or know your triangles. But we can do this. If we have the base of the triangle, we have the height of the triangle, we want to find the hypotenuse. We can do Pythagorean theorem. So very quickly here, a squared plus b squared equals c squared. From this, we're going to make a, since that's the base of the triangle, that 4 newtons. So 4 newtons squared plus 3 newtons squared equals c squared. 4 squared plus 3 squared is going to end up being 4 squared is 16. Plus 9 newtons squared equals c squared. So we have 25. Let me fix that 25. So we should have here 25 newtons squared equals c squared. Obviously take the square root of both sides, and c is going to be 5 newtons, which means that ft2 is equal to 5 newtons. So if you know your trigonometry, you saw that we had a 3, 4, 5 triangle there. But if you don't know any trigonometry, besides Pythagorean theorem, then that is some quick math to get to 5 newtons there. So let me fix this 9 here because it looks like a 4. So we have here that my FT2, my tension in the angle of strain, is going to be 5 newtons. So let's move into our last part here and get our actual angle. So we figured out here that Ft2y is equal to 3 newtons. We figured out that Ft2x is equal to 4 newtons. And we want to find the angle. So again, essentially we have a triangle here. So we found the hypotenuse, but we're not worried about that as much right now. We have both the legs, the base and the height. And we have an angle here that is with the horizontal. So we want to find this now. And essentially, we have the opposite here, which is that 3 newtons. And we have the adjacent, which is 4 newtons. So what trig function is opposite over adjacent? Last time I checked, that was tan. So tan theta equals opposite over adjacent. And all I want to do is solve for my angle here. So if you've ever heard of arc sine, arc cosine, or arc tan, the tan to the negative first in your calculator, all you do to get this is essentially you're dividing out tan from both sides because it's connected to the angle by multiplication. So when I do this here, this cancels, and it goes over to the other side as 1 over 10. In your calculator, you don't have that, so that's why you have tan to the negative first. So we should have here tan to the negative first. And again, my opposite here is 3 newtons, and my adjacent is 4 newtons. So you should be plugging into the calculator. Tan to the negative first times 3 over 4, or 0.75. Make sure your calculator is in degree mode. And we should get a pretty nice angle here. So we have here 0.75. And our angle is going to come out to be 36.9 degrees. So the angle here is 36.9 degrees. And if you had the proper apparatus, you could test this. And it should be well within range to show that physics is working properly. So again, our angle here is 36.9 degrees. Make sure your calculator is in degree mode if you're getting an improper number for that. So let's get into example number 2. So example number 2 is more of the same, but a little bit of a different situation. we have the 500-gram object hangs by two strings. So that's our mass M there in the middle. String 2 makes an angle of 39.8 degrees with the horizontal. And string 1 pulls along the x-axis. So we have a similar situation. But we are given different variables, essentially, or different parts of our question to then find the answer. So drawing the free body diagram, that's going to be exactly the same as before. So last time I checked, the force of gravity, or the force of Earth on this object is going to be straight down. So we're going to annotate this here on the side, force of Earth, because again, that is the object that is creating the force on the mass. Then we have here FT2. So FT2 is force of string 2 on the mass. And then we're going to have here FT1, which is going to be the force of string 1 on the mass. That's it. So again, same exact situation. We have the same exact free body diagram. Nothing's really changing with this besides the numbers that I'm given. Continuing to work with equilibrium. So again, we should have our forces balanced. We don't see currently a right force. We don't see currently an upwards force, but our force is at an angle, so it's going both up and to the right. So let's get into part B, where we break it up into our components. All right, so same deal here essentially as part B in example number 1. So again, if you want to follow along, it's in the description down below. So I'm going to draw out here what I have. No need to rewrite what all this means. So FT1, again, same exact deal. We break up our FT2 into our x and y components. Y, last time I checked for a graph, is the vertical axis. So that's going to be my vertical component. So we have here FT2y. And then going to the right here, I have FT2x. So essentially, again, we're going to create our equilibrium equation based on this. So very similar to the original situation, again, just given a different set of variables to kind of work with here. So let's go into part C again. So part C, create equilibrium equations for this object in both the vertical and horizontal directions. Again, this is being very similar, just to kind of get used to it. See, I'm going a little bit quicker with this to not completely bore you. So for this again, I'm just going to write out my free body diagram, or my diagram with the components. So again, the free body diagram is the original one that I did in part A. Part B is with components. You do not put components on the free body diagram. This is just to help you break up angled components, or when stuff's at an incline or anything like that. This is all you do this for. This is not the original free body diagram again. This is going to help me though make my equilibrium equations. So going straight down again, we have here FG. Going to the left, I have here FT1. Going upwards, I have here FT2y. And then going to the right, I have here, and I'll put it next to it, FT2x. So again, for equilibrium equations, as we've done here with 1D and now 2D, I have that my up forces equal my down forces. Oops. So my up forces again right now, based on the diagram that I have, that's going to be just FT2y, because there's only one going up, That's going to be equal to the one going down, which is the force of Earth on the mass. Then I'm going to have my left forces equal to my right forces. Oops. All right, so my left force here is going to be Ft1. That's going to be equal to Ft2x. So very similar situation here, but it is a tiny little bit different because we don't have certain things here that we had before. So now in part D, we're going to have to start solving for what we do not have here. So part D is going to be a little bit different from number one's part D. All right, so we're going to determine the tension in the angled string, and justifying the answers is showing the math here in this situation. So in our angled string right now, I do not have T1. So I really can't do much with that. What I can do is use my up forces equal to my down forces to kind of get my way towards that. So what I have here, so let's just show here up forces equal down forces. This will actually help me. Since I have the angle, I can do something with this. All right, so stay with me for a second because it's going to be a little bit odd while I'm just doing up forces equal down forces, but it's what I have at the moment. I can kind of work my way through this because I don't have string 1. I don't know what that is, but I do have an angle, and I do have what the actual mass is, the block there, mass M, which is 500 grams. So I can figure out my up force. That's one side of my triangle. I have the angle. I can do a little bit of trig to get the actual tension in the string. So we'll show this right now. So the up force here is going to be Ft2y. That's equal to Fg. And for Fg, we know Fg is equal to mg. Now I can start actually getting what Ft2y is. So we have here Ft2y. My mass is 500 grams. Divide that by 1,000 for kilograms here. So that's going to end up being 0.5 kg. My G is always going to be 10 newtons per kilogram. So I have here 10 newtons per kilogram. And what we're going to do with this is just multiply this together. Last time I checked, essentially this is half of 10. Last time I checked, that's going to be 5. But you're always checking your calculator just to be safe. So 0.5 times 10, that's going to be 5. So what we're going to have here for Ft2y is going to be equal to 5 newtons. So you're wondering why I did that. Right now, if I look at this again, it's essentially a triangle. I'm trying to find the hypotenuse here. What I just found is this side of the triangle. That's Ft2y. I have the angle. I'm trying to find my hypotenuse, which is just Ft2. Okay? So if Ft2y is 5 newtons, and I have an angle here of 39.8 degrees, and I have the opposite of that angle, what trig function is that going to be? It's going to be sine. The opposite of an angle is sine based on SOHCAHTOA. So I have here sine theta. So showing where my components actually come from here, sine theta is equal to opposite over hypotenuse. If I do a little bit of math here, when we go back to our facts, it's telling me that it's the force times sine theta. All I'll do is solve for opposite because I have that. So it's really hypotenuse of sine theta is equal to the opposite. And that's an opposite here, not 0. So let me write this out as actually opposite so we don't get confused here with 0. So my hypotenuse is Ft2. and I have ft2y. So what do I have to do to solve for ft2? Divide by sine theta. It's multiplied by ft2. They're connected by multiplication. You do the opposite, which is division, and you get your answer. So we're going to plug this in here, and I have here that then ft2 is equal to ft2y all over sine theta, and I was given these numbers. Well, I found ft2y, but I did not find theta. They gave me theta. So ft2y is just 5 newtons. Sine theta, my bad. Sine 39.8. Sine 39.8 degrees. We just plug this into my calculator. Again, make sure I'm in degree mode. Do 5 divided by sine 39.8, and you're going to end up with ft2 being just around 7.8. We'll have 7.81 because that's where it comes out to my calculator. And that's going to be my answer. So if I have a proper spring scale and set this up, I can get 7.8 newtons, just about. Or if I had a force sensor, which was perfect, it kind of jumps around all the time for that. But if you had a spring scale or a force sensor, you would get around that number because physics does work. So now, just do a little bit of trigonometry with this. That's where it comes from. So whenever you do this again, it's just where it's with the horizontal, opposite there, that's going to be ft, or the force, times sine theta. If it's the adjacent, it's the force times cosine theta. Just showing where this comes from through a little bit of trigonometry if you want to know. So now, part E is our last part here, and we're going to figure out the tension in T1. This is our last part here of the entire video. Like I said in the previous part, we're determining the tension. That will in turn give us the actual hanging mass provided here in the horizontal string. So it's kind of a 2-for-1 here with this. So we're just trying to find the mass that's actually giving us this. So if you work this in a classroom, essentially you put it on a pulley. There's a hanging mass there to make the actual tension in the string. It's the same exact tension as whatever the hanging mass ends up being here. So with this, we want to find the mass here. So doing our equilibrium here, now we're worried about our left and right forces. So trying to find the left force, so left forces equal right forces. So we can go one of two ways with this right now. Again, our left force here is ft1. Our right force is ft2x. Right now in our triangle, we have both the hypotenuse, we have the height, but we do not have the base. That's what we're attempting to find. So remember, our hypotenuse is ft2. Our height is ft2y, and that was 5 newtons. We have our angle. Our ft2 is about 7.81 newtons. And we have the angle here, which is given to us in the question. So there's a few ways we can go about this. Right now, I guess the easiest way to end up going about it, kind of give us the best number in this situation because it's a rounded off number with the 5 newtons. Let's deal with the 5 newtons right now. Since we have an angle and we want to find the adjacent to it, but we have the opposite, opposite over adjacent, that's tangent. So we're going to use tangent here. So tan theta, which equals opposite over adjacent. In this situation, the opposite is going to be ft2y, and the adjacent is going to be ft2x. Doing a little bit of algebra here, ft2x tan theta is going to equal ft2y, And then finally, let me move this over a tiny little bit, ft2x. Since we are attached to tan by multiplication, I want to do division. So let me show this actually. Let me fix this here. So over here, this will cancel. I'm going to have tan theta on this side. And what I did over here was multiplied ft2x to the other side. So I'll have here, let me move this over. I'm going to have here ft2x. That is going to be equal to ft2y all over tan theta. So now we can just plug in what we have here. So ft2y, that's 5 newtons. We know what tan theta is. So let's do our math here. So we have here ft2x is equal to ft2y is 5 newtons. Tan theta, that's tan of 39.8 degrees. And I just plug this into your calculator and we'll get our tension, and then in turn we're going to get our mass directly afterwards. So plug this in, 5 over tan of 39.8. That's going to give us 6 newtons. So you plug this in correctly, you should get 6 newtons here. So again, if you want to find a mass and you have a force that is based on the force of gravity, so we can go kind of back over here. Fg equals mg. You want to find the mass, you do whatever force you have here over g equals m. So we have here 6 newtons divided by 10 newtons per kilogram equals my mass. So plug this into your calculator and you should get around here 6 divided by 10. You should get 0.6 kilograms. So 0.6 kilograms is going to be my final answer. Again, you can test this if you have the proper apparatus in your physics classroom here. You should get pretty much the same exact numbers here as I have. All right, so I hope these examples were helpful. These are fairly long examples for trigonometry. It's probably the most intense the trigonometry gets in the entire year in AP Physics 1. There's a little bit as well in inclined planes, but as far as trig goes, these are like the longest trig questions you're going to end up having with two-dimensional tension and two-dimensional equilibrium and things like that. So I hope this was extremely helpful or helpful at all, and see you guys in class.